recapitulate, what happens if you don't have a magnetic field? It is something that we have already discussed in tight binding models, right? So what we want to, we have already introduced a tight binding model. I did it in my first lecture. Then BD has been talking about more complicated tight binding models, the Hubbard U, the hopping integral, etc., etc. So let me then try to connect to what I was discussing in the first day. We introduced the tight binding model. Remember, we built it up from this bottom-up approach. We took a simple two-level system, plus minus, bonding, anti-bonding states, and from that we create. Now you think of again a top-down approach, and you try to write down what is a single particle wave function for the whole crystal. So have an index k, the momentum k, psi kr is 1 over square root n. You sum over all lattice points, exponential I k dot rj. And remember the way we motivated the tight binding model. We said that suppose you have two hydrogen-like atoms, they are far apart. Each is described by a ground state wave function. This is Lagarde polynomials, but they go like exponential minus rho over k naught. And I try to bring them together, okay? Just these two atoms. When I bring them together, the wave functions start overlapping, right? Let me use another term. Okay, then the wave functions start overlapping. You don't know which electron is where. It's meaningless now to talk in terms of individual electrons. You only talk in terms of electron density, which is the probability of the wave functions mod squared. And then you find that you can, in fact, with these two wave functions, you can construct a symmetric state and an antisymmetric state. The antisymmetric state will have a node at the middle. The symmetric state has still an amplitude at the middle, and so therefore there is considerable probability of finding an electron density at the middle. So this is called the bonding state discussed. And this is called the anti-bonding state, the antisymmetric wave. Okay? And this model of, so this is what is called by Kittel, but a lot of other people, but Kittel's book has it, linear combination of atomic orbitals. And that's how you build the tight binding model. So Kittel shows that if you, from two atoms, you get a 20 atom situation. See what is happening here is that these two, these two levels, these two states are actually degenerate in energy, and when that degeneracy is lifted, when you bring them together, you have a splitting, and for 20 atoms, Kittel has given a picture of how you create bands, right? And this problem, as let me remind you, is very similar to what Mersbacher discusses, for instance, so it's called a double oscillator. This is just to remind you of the first day's lectures. At that time I was trying to motivate the simple tight binding model because BD was going to use it extensively. So the double oscillator is basically two back-to-back harmonic oscillators. Okay? Instead of having exponentially varying wave functions, now you have Gaussian functions with lowest harmonic polynomials, if you remember the harmonic oscillator-like wave functions. So the two lowest states are again symmetric and antisymmetric states. The psi 0 looks like this. So physically, this means that in the ground state, I have a finite probability of finding a particle here or there, and almost negligible probability of finding it in between if this barrier height is very large. And the first excited wave function looks exactly like what we drew before, the antisymmetric wave function. And then when you combine the two, you have, so Vipul, I checked, Vipul is on. Okay. So, but I should remind you that the discussion was that you plot it 2m omega h bar times A. So if this is A, this is minus A, this is plus A, And so if you take A to be very, very large, then you have two independent oscillators. So the levels are degenerate. When A is equal to 0, you have a single harmonic oscillator. So what you plot in the y-axis is n, which is En over h bar omega. Yeah. Right. So I think that day I was plotting something else. So I was writing n equal to 1, but this is actually n equal to, the first one is n is point, and then go on. And so this is 1, etc. And what you find is, but this is correct what I was saying, I saw it much better, that the energy actually goes down, and you have this distance collapse. So as A becomes very large, you have a doubly degenerate state, and in between, if you are, for instance, in this value of A, there is a tiny splitting, and that is what is called the tunnel splitting we discussed. And so you have this, the eigenvalues collapse in pairs. Okay? So the situation is very similar, except that you have now Gaussian wave functions. Okay? And so therefore, you have a multiple set of double oscillators. So if you just go on doing this, for the whole lattice, this is one version of what is called the Kronig-Penney model. Again, for the students, you go back and read Kittel, and you can see how a Kronig-Penney model can be exactly solved. You can get the band state. So it's a good, very good exercise for you. So if you put all of them together, you create the tight binding model. And so now, today what I want to write down is how you do this linear combination of atomic orbitals, and then you get psi of r minus rj. So you have constructed the wave function in such a way that the block theorem is automatically satisfied. What does the block theorem say? That my choice of coordinate system should be arbitrary. If I make a lattice translation of the r vector, then you change r to some r plus l vector. So here you change r to r plus l, but you can take the jth side to be at any side. So you make a change in variables. R plus L minus Rj, you call it new Rj, you stick that in here, and e to the ik dot L will actually be exactly equal to 1 because of the way you have chosen the values of k. K is, remember, 2 pi, the k has kx, ky, kz, and so you can use periodic boundary conditions. The block theorem is identically satisfied for this choice of the wave function. Is it all right? This has been discussed also by Professor D. Now, we can also use the Dirac notation. The Dirac notation says that your k ket vector is basically, this is a normalization constant, n is the number of sides that you have in the problem, j e to the I k dot rj psi j. So what is the meaning of the connection between this and that? So from this Dirac ket, you go to the Schrödinger ket by taking this inner product, and so that's just psi r minus rg. Okay? So now if I want to calculate, so what we have done is from the real space, we have gone into basically momentum space equivalent, and we want to ask the question, what is the ground state? So the ground state, you simply calculate the first order matrix elements of H between these two states. So you stick them in, so you get 1 over n now, the two square root n's. You have a sum over j and sum over m e to the I k dot rj minus rm times an integral over dr. dr is a three-dimensional volume integral, psi star r minus rn the Hamiltonian R H psi times R minus R. So now you know how to calculate matrix elements, right? And in terms of integrals over all space. So I just, it's a simple exercise. Please do that. I should not bore you with algebra. By simply making some change in integration variables and introducing a new rho m vector, which you define as Rm minus Rj. The reason my J index does not appear here, because lattice translation invariant says that I can choose my origin anywhere. So if you choose your origin at the jth side, then there is no J dependence. And this matrix element will turn out to be summation only over one index m. You get rid of one of the indices because of translational invariance. You get ik dot rho m, a phase factor, integral dr psi star r minus rho m h psi r. As simple as that. So this is just simple quantum mechanics, right? So the simplest tight binding approximation says that when you look at this integral, what you are doing, you are looking at the wave function at the point r, and you're taking the matrix element of the Hamiltonian, which is r, at another point which is shifted by the factor rho m. Okay? So simplest tight binding says that I can only have two non-zero matrix elements here, where rho m is either equal to 0, that is here at the same side, in real space the diagonal term, and rho m is one of the nearest neighbor vectors. So we are assuming, if we do assume, that we only allow hopping only over nearest neighbor sides. In DD's case, remember, he had a t, and then you also have a t prime, but as he always said, that t prime would be smaller than t prime would be non-nearest neighbor hopping. In many cases, t prime can be ignored. So if you only take nearest neighbor hopping, then you can show that you have actually only two non-zero matrix elements. One of them is dr psi star r h psi of r. You call that an energy minus alpha. This is a single site energy. And the nearest neighbor hopping will be dr psi star r minus rho, where rho is the nearest neighbor lattice vector, and you call that something like minus gamma. So in the this thing then will decompose into minus alpha, because when rho m is equal to 0, this will basically, this factor will go away, and you have a constant term, minus alpha minus gamma and summation m a to the power minus I k dot rho n, and that's what you call Ek, the energy. Now you can work out this energy, because all I have to do is to take this summation over nearest neighbors. Right? And so if I assume a simple cubic lattice, which is what DD was doing, you will get epsilon k. I'll keep everything on the board and pause and see if you have any question. So you simply do this sum and you will get cosine functions, right? Because associated with every plus rho m will also have a minus rho m, and so you'll get cosine functions and you'll get cosine. So I'm assuming a simple cubic lattice of lattice constant A. So remember, in DD's case, he was looking at one dimension, and you got factors like cosine KA, right? But in 3 dimension, with same lattice constant A, we assume it's simple cubic structure. And you can also say that if For instance, if you do an experiment in which your k vector, which is 2 pi over lambda in magnitude, the wavelength is larger than the lattice spacing, then you actually don't see the finite lattice anymore. And mathematically, it means that kxa is a quantity in magnitude much smaller than 1, and you can do a power series expansion. So cosine Ka will be 1 minus half k squared kind of thing. And so you'll get a dispersion relation, which will be like the free particle dispersion relation that BD was writing down. Epsilon k will scale like k squared, right? So these are the things that you've already seen before. And what now we want to do is to juxtapose the morning discussion, namely what happens in an Aharonov bomb phase, with this tight binding model and see what happens. Okay? Yep.
So you're saying that I'm a bit curious about this expansion which you mentioned. So depending on where, if it is half filled, if I expand, the first term will be a linear term. If I go to the edge of the band, completely filled band or completely empty, then it will be more like k squared. How do I kind of understand that intuition and put it together?
In the Brillouin zone, you can look at it. Different experiments will have different k values at your disposal.
Right. Yeah.
And so with
with the filling, you are saying, am I making already in this statement an inbuilt filling statement also? Where I am, where my Fermi energies, am I making a statement?
No, at this stage we are not worried about this at all. I mean, I have a single electron problem and periodic lattice. Now you go to B not equal to 0. You have a magnetic field. So what you are saying is that you have something like graphene, you have a tight binding model, and now the lattice then threads a magnetic field, threads magnetic flux. So what did we see earlier? See now, your K, the Dirac K that I wrote down here, will acquire another additional phase factor. Remember what we said in the morning, that Aharonov bomb effect means that even if there are regions in which there is no magnetic field, the vector potential field exists, and there's a net phase difference when the electron beam passes through those regions. And we calculated that. It turned out to be e to the power IE over h bar c, the flux quantum divided, then A dot dl, the line integral of the vector potential with dl. So every lattice site now, the phase acquires an extra factor due to the Aharonov bomb effect. And so now I have the Dirac kit as function j e to the I k dot rj and e to the I phi j. So let me write it in a different color code just to emphasize that this is something new that came up which you might not have seen before, because normally it doesn't appear in any course in quantum mechanics that I have seen this country at least. Maybe if you're in Israel you'll see it, but not here. There's a lot of Aharonov bomb stuff there. So this is coming because of the AD. Okay? Right? This is what we saw before. So what does our tight binding model Hamiltonian now look like? HDB. Remember, we had a site energy earlier, both in my lecture as well as in DD's lecture, epsilon L, L, L. And then you have minus summation Ln. I will assume nearest neighbor hopping only to be in the simplest situation. So that is why we indicate that by having angular brackets over the summation indices. This is standard notation in physics at least. And then you have your hopping terms. Okay, so we call it T. So let me call it T. TLM. Okay. These are this projection like operators plus Hermitian adjoint. This is what the tight binding model that I wrote down, DDM amplified. But now what you did not have before is the fact that there is a phase change coming from the Lth ket vector into the I phi L phase change coming from the mth vector, and so the net phase change appears here, so it is I phi ln, and this is again due to the Aharonov thing, so phi ln is defined as the difference between phase at the lth side minus the phase at the mth side. Ask the question, how does it depend on the magnetic field? So phi L, if you remember, will be the, when you have the magnetic field on, you have to calculate the line integral of the vector potential. We'll do that shortly and show you how you actually get the flux threading a triangle that you can construct out of the RL vector and the Rn vector. That we'll do shortly. So, this was already, it was part of my first part of the talk. So let me just ask the students first. Any question? Yeah.
So the magnetic field is perpendicular to the sample. What if the magnetic field parallel to the...
Yeah, so the, all right, good question. So if I have a magnetic field along the z-axis, and electron moving randomly, let us say, remember that only the electrons in this plane will be affected because of the Lorentz force being V cross B. Okay? So, so therefore, along the direction of the magnetic field, the problem continues to be like that of a free particle. In plane, you have the Lorentz force. You have to take the V cross B component. V cross B will be perpendicular to the direction of the B field. And that's why the physics is now a two-dimensional physics. Right? So diamagnetism problem is a two-dimensional phenomenon. Right? So if you think of something like a planar, something like a graphene system, where you actually, it's a nano system because you have no translational invariance on the other side. All right? In that sense, you have broken translational invariance. And you think of the magnetic field to be applied like this. So the graphene layer, let's say, is in the xy plane. You apply the field along the z-axis, and your activity is now in this plane. Yeah? Sorry.
Okay. So you are, I thought it is something like over a bond I can define a small a dot d.
Yes, that's what I'm doing. Over the bond, which is the LMF bond.
So this, what you're saying, flux is not yet flux. But once you close the loop, of course, you get something gauge invariant, and that's. Like
I'll show that immediately.
Okay, this probably is gauge invariant. This number is still gauge dependent.
It's gauge dependent now, but when I calculate something like a bond current, then of course it's a physically measurable quantity, and it should not have any gauge. So, just to again get to this point, you see, your Hamiltonian that you write, or Lagrangian that you write, I mean Lagrangian even in classical mechanics, first chapter of Goldstein, you'll find that when I have a charged particle in a magnetic field, your Lagrangian, what is a Lagrangian? Lagrangian is kinetic energy minus the potential energy. Chemistry wala ke Lagrangian nahi jante ho kya? Acha, okay. So, because you graduate. When you do mechanics, you first start with Lagrangian. Then Lagrangian comes back to you when you do quantum field theory and things like that. But then, when you did ordinary quantum mechanics until 1930s, we used the Hamiltonian picture, where in the Lagrangian picture, your fundamental variables, so look, I'm saying very elementary things, but it's good to remember this. You deal with Q, Q dot, and T. You graduate to Hamiltonian mechanics, instead of Q dot, you start talking about a canonical momentum T. Okay? You start talking about canonical momentum, and from Lagrangian, then you make a Legendre transformation to get to the Hamiltonian, like PIQI dot करके. Now you have to do this exercise very carefully when you have a magnetic field. And you'll find